Hello students, today we are going to study the basics of packaging and cooling in electronic components and devices. The motherboard and various other printed circuit boards are electronic components of a desktop system. When the desktop system is under operation, heat is generated by the electronic components and the power supplies. If the heat is not removed, it may lead to increase in the temperature, especially in the countries having hot climates. The temperature increase causes malfunctioning and failure of the electronic components. The overheating is the major cause of failure in the electronic components. Even the most reliable and well designed electronic device can malfunction or fail if it overheats. The heat generation and the thermal issues are incorporated in the design of electronic components since the early stages of the design process. The electronic component suppliers estimate that for every 10 degree centigrade rise of the junction temperature, the device failure rate doubles. If the waste or the excess heat generated inside a package or the device is not removed, the reliability of the device is compromised. Therefore, it is essential that the desktop system should have a cost effective cooling system that takes away the excessive heat from the system and keeps the temperature within the limits. The objective of the today's lecture is to understand the basics of the heat generation and incorporating effective cooling systems to keep the temperature within limits. As we all know that the cooling systems play a crucial role in reliable and error free functioning of the electronic components. The heat generated by the electronic devices and circuitry must be dissipated to improve reliability and prevent premature failures. The various techniques for heat dissipation are heat sinks and fans for air cooling and other forms of cooling such as liquid cooling. In cases of extremely low environmental temperatures, it may sometimes be necessary to increase the temperature by heating the electronic components to achieve the satisfactory operation. Various cooling methods which are available are keeping electronic devices within their operating temperature specifications. Let us start first with cooling consumer products. In the case of consumer products such as kitchen appliances and telephones, the cooling mechanisms are simple and static. The cooling is limited to thermal conductivity of the packaging material and natural airflow inside the devices. The airflow is made available through thin openings of the box packaging these devices. Also, the overheat protection mechanism is provided which temporarily shuts off the device if the temperature goes beyond limits. After waiting for few minutes, we can again start the normal operation of these consumer products. The overheat protection mechanism indicates the overheating of the system due to malfunctioning or excess running. Also, it saves the critical components of the appliances from major failures. For other products such as desktops, servers or supercomputers, there are many ways to remove heat from a device, from placing the device in a cool spot in the enclosure to using a liquid cooled plate connected to a refrigerator water chiller. The amount of heat generated by the device, the package configuration and the expected lifetime of the product combined with various other cost factors determine the optimal heat removal schemes. One of the primary cooling mechanisms is to use the natural air currents. The electronic components are generally hosted in a metallic box. The thin openings, ventings are provided in the metallic box for natural air currents. If the natural air current is enough to keep the temperature under control, it can save on long term component cost. Using a computer modeling package, a designer can experiment with component placement and the addition of the enclosure venting to determine the extent of cooling through natural airflow. The testing can be performed under various outside climatic conditions prevailing in the region over the year. When these solutions fail to cool the device sufficiently, the addition of a fan is often the next step. The next cooling mechanism is the use of enclosure fans. The mounting of fans over the electronic components provide cost effective mechanism of cooling and extracting heat from these systems. Increased airflow lowers the temperature of any critical device and provide required cooling for all the devices in the area. Increased airflow also improves the cooling efficiency of the heat sinks. Even a low cost material with low thermal conductivity used in heat sink can perform effectively with a fan. However, the mechanical operation makes the fans less reliable than the passive system. In a battery powered application such as a notebook, computer, the power consumption by the fan can reduce the battery life, reducing the perceived quality of the product. Also, the failure of fan due to jerks or any other mechanical reasons can fail the entire system. Despite these drawbacks, fans have proved to provide efficient and reliable cooling for many applications and therefore are commercially popular. The fans are also mounted over microprocessors used in most of the desktop computers. The sound coming out of a cabinet unit is because of the fan operation. The next cooling mechanism is passive heat sinks. The passive heat sink use a mass of thermally conductive material to move heat away from the device into the air stream where it can be carried away. The heat sink contains fins to increase the surface area, thus increasing its ability to remove heat from the device. Segmenting the fins further increases the surface area to get more heat removal. The passive heat sinks optimize both cost and long term reliability. Also, the elimination of the fans lead to a silent system. The mobile devices use passive heat sinks to extract heat generated by integrated circuits and battery during the charging process. When a passive heat sink cannot remove the heat fast enough, a small fan is added directly to the heat sink itself, making the heat sink an active component. These active heat sinks often are used to control and cool microprocessors, provide a dedicated airstream for a critical device. The active heat sinks often are a good choice when an enclosure fan is impractical. As with the enclosure fan, active heat sinks carry the drawbacks of reduced reliability, higher system cost and higher system operating power. The next cooling mechanism is use of heat pipes used for quick cooling. The heat pipes, a type of recirculating system, use the cooling power of the vaporization to move heat from one place to another as shown in the figure. Within a closed heat removal system such as a sealed copper pipe, a fluid at the hot end near a device is changed into the vapor. Then the gas passes through the heat removal area, typically a heat sink using either air cooling or liquid cooling techniques. The temperature reduction causes the fluid to recondense into the liquid, giving off its heat to the environment. A heat pipe is a cost effective solution and it spreads the heat uniformly throughout the heat sink condenser section, increasing its thermal effectiveness. The next mechanism for cooling is metal backplanes. The metal core printed circuit boards, stamped plates on the underside of a laptop keyboard and large copper pads on the surface of a printed circuit board all employ large metallic areas to dissipate heats. A metallic core circuit board turns the entire substrate into a heat sink, augmenting heat transfer when the space is at a premium. While effective in cooling hot components, the heat spreading of this technique also warms the cooler devices, potentially shortening their lifespan. The 75% increase in the cost over conventional substrates is another drawback of metal core circuit boards. When used with a heat pipe, the stamped plates are a cost effective way to cool laptop computers. The stamped aluminum plates also can cool power supplies and other heat dissipating devices. The thermal interfaces are another way of cooling the devices. The interface between the device and the thermal product used to cool it is an important factor in the thermal solution. For example, a heat sink attached to a plastic package using double sided tape cannot dissipate the same amount of heat as the same heat sink directly in contact with a thermal transfer plate on a similar package. The microscopic air gaps between a semiconductor package and the heat sink caused by the surface non-uniformity can degrade the thermal performance. This degradation increases at the higher operating temperatures. The interface materials reduce the variability induced by varying surface roughness, since the interface thermal resistance is dependent both upon the applied force. The contact pressure becomes an integral design parameter of the thermal solution. If a package or device can withstand a limited amount of contact pressure, it is important that the thermal calculations use the appropriate thermal resistance for that pressure. The chemical compatibility of the interface materials with the package type is another important factor which is considered while selecting the interface material. In other words, the interface material should not chemically react with the package. There are various thermal options for different packages and applications. Many applications have different constraints that favor one terminal thermal solution over another. The power devices need to dissipate large amounts of heat. A thermal solution for the microprocessors must take space constraint into account. Surface mount and ball grid array technologies have assembly considerations. The notebook computers require efficiency in every area, including space, weight and energy uses. While the optimal solution for any one of these packages type must be determined on a case by case basis. Some solutions address specific issues, making them more suitable for a particular application. Next, we discuss the various applications and devices where cooling mechanisms are used. One such device is personal computer. Since last 2 decades, lot of technological advancements have taken place in the central processing unit, which is called CPU in short. The number of transistors, speed, clock rate, number of instructions, size of on chip cache and the number of registers on the central processing unit have increased many-fold. In the early 2000s, CPUs were produced that emitted more and more heat than earlier. The increased clock rates have led to faster performance. However, the faster performance comes at the cost of increased power consumption and dissipation. The technology is needed to effectively extract the heat from the CPU and keep the temperature within limits for reliable and error-free operation. The use of the active heat sinks allow concentrated dedicated cooling of the microprocessor without severely impacting the space requirements. Generally, active heat sinks like fans are used for cooling desktop personal computers and microprocessors. The another type of device generating heat are power supply devices. The devices incorporate a heat transfer plate on the bottom of the device, which are wave soldered directly to the printed circuit board. The metal core substrates offer a potential solution to the power device cooling and are commercially popular in desktop systems. Next, the cooling in the notebook computers. The notebook computers have space and other constraints. The multiple constraints of the notebook computers demand consideration of nearly all types of heat removing devices separately and in combination. The notebook, including the metallic body cover, is designed in a manner that the heat coming out from CPU or battery charging is taken away through airflow currents through natural airflow. If the natural airflow is not found sufficient, fans are mounted to keep the temperature within limits. Another application of cooling mechanism is the use of temporary heat sink. While soldering the electronic components on the printed circuit boards, these temporary heat sinks prevent excessive heat from damaging the sensitive nearby electronics. In the simplest case, this means partially gripping a component using a cooling mechanism, so that the heat generated from soldering does not destroy the nearby components. The modern semiconductor devices can usually tolerate soldering temperatures without damage. On the other hand, the electrical components such as magnetic reed switches can malfunction if exposed to higher powered soldering irons. So, this practice is still very much in use. The next device where cooling is needed is the battery. In the battery used for electrical vehicles, the nominal battery performance is usually specified for working temperatures somewhere in the plus range of 20 to 30 degrees centigrades. However, the actual performance can deviate substantially from this if the battery is operated at higher temperature or in particular lower temperatures. So, some electrical cars have heating and cooling for their batteries. The learning outcome of the today's session can be described as the various cooling mechanisms we have learned. We have learned various cooling mechanisms to keep the temperature of the electronic systems within acceptable limits. The mechanisms explained were cooling through fans, active and passive heat sinks, heat pipes and metallic backplanes. The controlling temperature is essential for reliable and error-free operation of these systems. These cooling mechanisms are incorporated in these systems early in the design process. Any ad hoc arrangement done later not only adds extra cost, but also requires more space and sometimes may not be very effective, leading to other design constraints. By considering all the options during the initial board design, the system designer can reduce the overall thermal management cost, optimize the board layout and maintain high system reliability by adopting one of the cooling mechanisms as explained. Thank you.